150 and 180 would be 30 degrees. So I could say that the reference angle is 30 degrees. This reference angle and the cast rule is going to help me find the sine ratio for 150. And as a reminder, the cast rule tells me that in quadrant number 2, where the terminal arm is, the sine ratio is positive. For that reason, I know that sine of 150 is going to be equal to the positive sine ratio of the reference angle. So it'll be equal to sine of 30 degrees. And from my special triangle, I know that sine of 30, well, sine means opposite over hypotenuse. So sine of 30 is 1 over 2. So my final answer for sine of 150 is that it's equal to a half. Let me take a second and explain to you why sine of 150 is equal to sine of 30. If I were to draw a principal angle of 30 degrees, that would mean rotate 30 degrees counterclockwise from the positive x, and that will land you in quadrant number 1. The reference angle is 30 degrees, and if we look at where both of those terminal arms intersect the unit circle, if we look at the points where those terminal arms intersect the unit circle, notice that they have the exact same y-coordinate. And if you remember, if we look over here, the y-coordinate of where we intersect the unit circle is equal to the sine ratio of the angle. So of course sine of 150 and sine of 30 have the same value because they intersect the unit circle at 2 points that have the same y value. And the y value of those points would of course be a half. Let me do one more example quickly for you. I'll shrink this to make room. Let's find cosine of 225 degrees. I'll start by drawing my Cartesian grid and figuring out where 225 degrees falls. If I were to rotate 225, I would go past 180 into quadrant number 3. So the principal angle is 225. And the reference angle, which is the angle between the terminal arm and the closest x-axis, so the angle between 225 and 180, is 45 degrees. And don't forget, based on cast rule, in this quadrant, only tan ratios are positive, which means any cosine ratio of an angle in that quadrant will have to be negative. So I can change the principal angle of 225 to the reference angle of 45 as long as I make the cosine ratio negative. So I can say this equals the negative cosine of the reference angle 45 degrees. And cosine of 45 from your special triangle, you would notice cosine is adjacent over hypotenuse. So I would have negative 1 over root 2, which if I rationalize that would be negative root 2 over 2. That would be the exact value of cosine of 225. There you go. Now you know how to use your special triangles, the unit circle, and the cast rule to find exact values for trig ratios. Must know number 7. Sine and cosine as functions. Let's start with sine. If we were to think of sine as a function, so y equals sine x shows the relationship between x, which is our angle, and y, which is equal to the whole sine ratio of the angle. We could create a bunch of xy pairs and graph and see what the function looks like. So that's what I'll do. I'll make a table of values where my independent variable x are going to be angles and the y values are the sine ratios of those angles. The angles that I'm going to pick are at 90-degree intervals starting at 0. So 0, 90, 180, 270, 360. In order to figure out the sine ratios for each of these angles, it'll be helpful if you remember the unit circle. Based on the unit circle, hopefully you remember that the point where we intersect the unit circle, the x-coordinate tells us the cosine ratio for the angle and the y-coordinate tells us the sine ratio for the angle. So if I want sine of 0, I look if the terminal arm intersected the unit circle at 0 degrees, the y-coordinate would be 0. So sine of 0 is 0. And then just continue looking at the y-coordinates as you rotate around the unit circle, and you would figure out the sine ratios go 0, 1, 0, negative 1, 0. And if this terminal arm kept rotating around, we're going to have that same pattern of y values that just keeps repeating over and over again. That's why this is called a periodic function. It has a pattern of y values, which we see here, that just repeat over and over again. Let me graph that for you. If I plot the 5 points that I have in my table, I get one cycle of this sine function, and it looks like a wave that oscillates up and down between y values of negative 1 and 1. If I were to continue this pattern, I would get another cycle of this function. The domain of this function is infinite. This pattern just keeps continuing forever in both directions. Let me now show you what a cosine function looks like. So I'm just going to shrink this so I have room. Let's graph the function y equals cosine x, where the x value is the angle and the y value is the cosine ratio of that angle. I'll choose the same x values, and to get the y values, I can just look at the x coordinates as I rotate around the unit circle, since that's what the cosine ratio of the angle is equal to. So as I rotate around, my x values are 1, 0, -1, 0, and 1. And that pattern of y values would continue. This will just give me one cycle of the graph. And let me show you that. If I wanted another cycle, I would just continue the pattern. Let's talk about a couple key properties of these graphs. The two things we need to look at are things called the amplitude and period of these functions. The definition of amplitude is that it's half the distance between the max and min y values of a periodic function. Well, for both sine and cos, the maximum y value is 1, and the minimum y value is -1. So the full distance between max and min is 2, half of that is 1, therefore the amplitude is 1. The period of a periodic function is the horizontal length of one cycle. If I map off one cycle of sine and one cycle of cosine, notice the horizontal length of both of those cycles is 360 degrees. There you go. Hopefully you now understand how we could think of sine and cosine as functions, and you have a general idea of what the graphs look like. Must know number 8, radians. Up until now, all the angles we've been working with were measured in degrees. But there's another unit of measurement we could think about for angles, and that is radians. Let me show you what a radian is. If I draw a circle, it'll help you visualize it. Let me draw an angle that subtends an arc length of this circle. In this circle that I've drawn, I have the radius here, and this right here is what we call the arc of the circle. If we were to measure this angle in degrees, we would just figure out how many 360ths of this circle this section occupies. But if we're going to measure it in radians, we're going to figure out how many radiuses have we moved around the arc of this circle. And how we figure out how many radiuses we've moved around the arc is we use the formula, the arc length, divided by the radius. So whatever the ratio of this arc length divided by this radius is, that's the measure of that angle in radians. So what does 1 radian look like? Well, if this arc length was exactly equal to the length of this radius, that would be 1 radian, right? In the angle calculation, when we do arc over radius, if the arc and radius are equal, really what I'm doing is the radius divided by the radius, which is of course 1. So how many radians are in a full circle? Well, do you remember the relationship between the circumference of a circle and its radius? The relationship is that the circumference equals 2 pi times the radius. So that tells us that the radius fits around the circumference of the circle 2 pi times. Therefore, there are 2 pi radians in a circle. So in a circle, we could say there's 360 degrees or 2 pi radians. Those are equivalent to each other. So let's pick a common degree to convert to radians. How about 30 degrees? If I want to convert it to radians, well, how many radians are in each degree? In this equation I made here, let's change this 360 degrees to 1 degree by dividing both sides by 360. If I do that, you'll see that 1 degree equals pi over 180 radians. To change 30 degrees to radians, I would have to multiply by pi over 180. 30 divided by 180 reduces to 1 over 6, so this would equal pi over 6 radians. So all of the trigonometry that we did up till now in degrees, we could easily convert all of it to radians by just multiplying any degree measure by pi over 180. Must know number 9, trig identities. First of all, what is a trig identity? A trig identity is an equation that is true for all values of the variable. And there are 3 fundamental identities that you should be familiar with: the reciprocal identities, the quotient identities, and of course the Pythagorean identity. The reciprocal identities are that cosecant of any angle is equal to the reciprocal of, so 1 over, sine of that same angle. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. The quotient identities tell us that tan x is equal to the quotient of sine x and cos x. And since cotangent is the reciprocal of tangent, that must mean that cotangent is the reciprocal of sine over cos, which is cos over sine. And the Pythagorean identity is that sine squared of x plus cos squared of x equals 1. And there are common ways to rearrange that. Now, any of these equations are true no matter what value of x you sub in. So sub in anything you want for these x's into sine squared x plus cos squared x, and it's always going to equal 1. Now, what we can do with these identities is prove other identities. So let me make some room, and then we'll prove an identity. Let's see if we can prove that tan squared x minus sine squared x is equal to sine squared x times tan squared x. If this is an identity, it'll be true for all values of the variable. So how we prove that is separating into left side and right side of the equation, and work with both of these sides completely separately from each other. So I'll draw a line down the middle and start rewriting these expressions in equivalent ways to reveal that they are in fact the exact same expression. So I'm not allowed to change the value of either of them. What I could do on the left, I know that based on the quotient identity, tan of any angle equals the quotient of sine over cos. So I can change tan squared x to sine squared x over cos squared x. And then I'm subtracting sine squared x, but remember that sine squared x is technically over 1. I can multiply top and bottom of that by cos squared x to get a common denominator. I haven't changed its value, I've just multiplied it by 1. So now I have a common denominator of cos squared x with both of those terms, so I can combine those into a single fraction. In the numerator, I have two terms, and both of those terms have a sine squared x, so I could common factor that out. And now I have a quotient of sine squared x and cos squared x based on the quotient identity. I know that that's equal to tan squared x, and that's being multiplied by a 1 minus cos squared x, which based on the Pythagorean identity, I know is equal to sine squared x. And now notice, that's the exact same expression as I have on the right side of the equation. So the two sides of this equation are actually the exact same expression. They're exactly equivalent to each other for all values of x. So we've proven the identity. We can say left side equals right side, or QED. Must know number 10, solving trig equations. I'm going to give you two trig equations to solve. The first one is sine x equals negative 1 over root 2. And for this one, I only want the solutions between 0 and 2 pi, which means only the solutions in the first cycle of this function. Since sine is a periodic function, there's going to be an infinite number of times it's equal to negative 1 over root 2. So by restricting the domain, I'm only asking you for two of the answers in this case. So let's go ahead and find those two answers. You're going to have to remember your special triangles, so let me draw those off to the side. When solving a trig equation, I like to draw a Cartesian grid, and based on cast rule, I like to figure out where my answers are going to be. Since the sine ratio is negative, I know sine ratios are negative in two quadrants, in quadrant 3 and in quadrant 4. So I'll place a terminal arm in both of those quadrants. In order for the angles that get to these terminal arms to have the same sine ratio, I know that those terminal arms must have the same reference angle. And what is the reference angle that creates a ratio of 1 over root 2? Well, sine of pi over 4 equals opposite over hypotenuse 1 over root 2. So I know the reference angle for both of these terminal arms is pi over 4. And now I just have to calculate the two angles that get to those terminal arms. So my first angle, I'll call this x1. I'm looking for the angle that goes from positive x counterclockwise all the way to that terminal arm. Well, notice it went past pi by pi over 4. So I could say that x1 is equal to pi plus pi over 4. Which is 5 pi over 4. And to get to x2, I would have to go not a full 2 pi, I would have to go pi over 4 less than that. So I can do 2 pi minus pi over 4 to get my second principal angle. And 2 pi minus pi over 4 is 7 pi over 4. So there are two answers to this equation between 0 and 2 pi. The answers are 5 pi over 4 and 7 pi over 4. Let's do a second equation where I don't restrict the domain. Let's say we have 2 sine squared x minus 3 sine x plus 1 equals 0. I would start by factoring this quadratic expression by finding numbers that have a product of 2 times 1, so a product of 2, and a sum of negative 3. The numbers that satisfy that product and sum are negative 2 and negative 1. There's lots of factoring methods you could use. I'll just split the middle term of this quadratic into negative 2 sine x minus sine x. And now I would factor by grouping. I would take a 2 sine x from the first two terms and take a negative 1 from the last two terms. I can take out this common binomial of sine x minus 1, and after I take that out, I'm left with 2 sine x minus 1 as my second factor. Now this product would be 0 if either of these factors were 0. The first factor would be 0 if sine x was equal to 1, And the second factor would be 0 if sine x was equal to a half. Now, sine x equaling 1, if you know your unit circle, that answer will be easy. If you rotate an angle of pi over 2, it intersects the unit circle at a y-coordinate of 1, and I know the sine ratio is equal to the y-coordinate, so the angle that would make the sine ratio be 1 is pi over 2. So the first answer to this equation is pi over 2. Now, because the domain of this equation has not been restricted, I know that I could continue rotating around this circle, and every 2 pi radians I rotate around, I'm going to be back intersecting at that same point. So how I could communicate that is I could say that I can add 2 pi k times, where k has to be an integer. So there's a set of answers that come from the first factor being 0. Now, how can this second factor be 0? Let me draw a quick Cartesian grid. I have a positive sine ratio. Well, sine ratios are positive in quadrant 1 and 2. So there'll be a terminal arm in both of those quadrants. Both of those terminal arms have the same reference angle, and the reference angle is going to be pi over 6. And I know that because sine of pi over 6 is 1 over 2, opposite over hypotenuse. So I'll place the reference angle of pi over 6 in both of those quadrants. And now I have to calculate the principal angle to get to each of those terminal arms. In quadrant 1, the principal angle is just equal to the reference angle, so it's pi over 6. And my second terminal arm, which is my third answer for x overall, to get to there, I would go pi over 6 less than pi. Pi minus pi over 6 is 5 pi over 6. And from either of those terminal arms, you could rotate 2 pi radians and be back to the same spot. So to communicate that, I would say to either of these answers, I could add 2 pi k, where k has to be an integer. So these 3 sets of x values give me all the solutions to this original equation. Hopefully this video helped you gain more confidence in your understanding of trigonometry. Let me know about what you want a top 10 of next.
Jensen